chemists often perform reactions in solution or deal in some other way with chemical species in solution. So it's important to understand how we express the concentrations of solutes in solutions. Today we're going to talk about one of the most common ways of expressing solute concentration, namely molarity. To get started, let's remind ourselves about a little chemistry lingo, namely about two words, solute and solvent. The solute is what gets dissolved. The solvent is what the solute is dissolved in. For example, if I dissolve table salt in water, the solute is sodium chloride. The solvent is water. Okay, now as the name implies, the molarity of a solution is defined as the number of moles of solute in 1 liter of solution. Now, by way of quick review, let's recall that a liter is a unit of volume about the size of a quart. It's essentially a European quart.
Mais oui.
You're probably used to buying pop in 2-liter bottles like this one. So a liter is about half that much. Now, if in this liter of water I had, say, 0.005 moles of potassium nitrate, I would say that the molar concentration of potassium nitrate is 0.005 molar. Or I might well say, this solution is 0.005 molar in potassium nitrate. Someone else might say, the molarity of the solution is 0.005 in potassium nitrate. Now, as usual, we have shorthand ways of writing this information. First, we can use square brackets to signify molar concentration. For example, this symbol, potassium nitrate in square brackets, means the molar concentration of potassium nitrate. And the unit, moles per liter, is written capital M. So in our example case here, we would write this, and we would read it. The concentration of potassium nitrate is 0.005 molar, or in other words, 0.005 moles per liter. So how would I go about making a 0.005 molar solution of potassium nitrate? Well, let's go in the lab and find out. To make our solution precisely, we're going to need 2 specialized pieces of equipment, a fairly sensitive balance, and a special kind of flask called a volumetric flask, or vol flask for short. This particular vol flask is a 1-liter vol flask, so that should make our job fairly straightforward. Now, if I want to make a 0.005 molar solution, which is 1 liter in size, how much potassium nitrate will I need? That's easy. I'll need 0.005 moles of potassium nitrate. Now, of course, I don't have a device that will count out 0.005 moles of potassium nitrate for me, so I'm going to want to weigh out 0.005 moles. And I can do this because I know the correspondence between numbers of atoms and weight. Specifically, the molecular weight, or more correctly, formula weight, of potassium nitrate tells me how much 1 mole of potassium nitrate weighs. And I get that molecular weight from the periodic table. The molecular weight of potassium nitrate is given by 1 times the atomic weight of potassium, plus 1 times the atomic weight of nitrogen, plus 3 times the atomic weight of oxygen. And that equals 101.1032. Now that's the weight in grams of 1 mole of potassium nitrate. But we want the weight of 0.005 moles. So we multiply to give 0.5055 grams. The idea is that if I now weigh out 0.5055 grams of potassium nitrate and dissolve it in enough water to make 1 liter of solution, I'll have a 0.005 molar solution of potassium nitrate. I'm going to go ahead and weigh that out right now. Okay, here's our 0.5055 grams of potassium nitrate. I've weighed it accurately to 4 decimal places. Now I'm going to call into action our second specialized piece of equipment, this vol flask. Notice that the flask has a tall, thin neck with a mark etched into the glass right here. You probably can't see it. Trust me. If we fill up the flask carefully just to that mark, we have exactly 1 liter of solution. So I pour the potassium nitrate into the flask. Then I begin adding water. Once the flask is about half full, I swirl until the potassium nitrate is dissolved. Then I add water up to the mark. There, our solution is done. Now you might well ask, why not weigh out the potassium nitrate, then measure out the 1 liter of water in the vol flask, and then mix the two? Well, it turns out there's a good reason why this won't work. Remember that the definition of molarity is moles per liter of solution, not solvent. And the solution consists of both the solute and the solvent. The solute, in this case potassium nitrate, adds some volume to the solution as well as the solvent. So we have to make the solution this way so that the volume of the whole solution, including both solute and solvent, is 1 liter. You may also ask, why did I stop when the flask was half full to dissolve the potassium nitrate? Why not just fill it up right from the start? Well, this question brings to mind an interesting feature of solutions. A typical solvent, like water, is composed of molecules like this. Notice that there are spaces between the molecules. Solute molecules may partially fit into these spaces. So when we mix a solute and a solvent, the volume of the resulting solution does not usually equal the sum of the volume of the solute plus the volume of the solvent. And so, to get a good volume reading for the solution as a whole, I have to dissolve the solute early in the process. Get it? You might also wonder about the effect of temperature on making a solution like this. And you'd be right to wonder. The volume of things changes with temperature, doesn't it? So in fact, the vol flask we used was calibrated to be 1 liter at our normal room temperature. If we were making the solution in Death Valley in July, or at the North Pole at any time of year, we'd have to adjust the concentration by taking into account the way the volume of water and of the glass change with temperature. And this is one of the weaknesses of using the molar concentration unit as opposed to a unit based only on weights. With the molarity scale, the concentration changes with the temperature. Just keep that in mind, okay? There's one particular nuance of solution concentration that's critical for you to understand. It has to do with what happens when solutes dissolve to form ions. Potassium nitrate is a perfect example of what I'm referring to. When potassium nitrate dissolves, it doesn't exist in solution as KNO3 molecules or units. Think about it. What kind of compound is KNO3? Ionic or covalent? It's ionic, right? It consists in the solid crystal of potassium ions and nitrate ions stacked together. So when potassium nitrate dissolves in water, the ions separate from one another in the solvent. We say KNO3 is a strong electrolyte for this reason. That is, when it dissolves in water, it separates into ions, and the resulting solution conducts electricity. Well, what does that say about the way we express the concentration of species like KNO3? When we say that the concentration of potassium nitrate is, let's say, 1 molar, we're simultaneously saying that the concentration of potassium ions in the solution is 1 molar. And we are saying that the concentration of nitrate ions in the solution is 1 molar too, aren't we? Well, that's all rather obvious and unimpressive, but let's go to a harder example. Take magnesium chloride. When it dissolves in water, each MgCl2 unit produces 1 magnesium ion and 2 chloride ions. So think now. If the molarity in the solution is expressed as 1 molar in magnesium chloride, what is the molarity of magnesium ions? Well, clearly it's 1 molar, because every magnesium chloride unit produces 1 magnesium ion in solution. But what is the molarity of chloride ion? It's 2 molar, because every magnesium chloride unit produces 2 chloride ions. So the concentration of the solution depends really on how we ask the question, doesn't it? If we ask, what is the concentration of magnesium chloride? It's 1 molar. If we ask, what is the concentration of magnesium ion? It's 1 molar. But if we ask, what is the concentration of chloride ion? It's 2 molar. Now just one final note on this topic before we move on. Not all solutes dissolve to produce ions. Ionic compounds generally do, whereas covalent compounds sometimes do and sometimes don't. Acids like HCl do, that's a covalent compound, but alcohols, which are also covalent, don't. One of the great things about molarity is that chemistry teachers can create all kinds of ingenious test questions with it. Why don't we try a couple of fairly simple ones together with Brian here, so you'll be ready to do some harder ones later on. Actually, this kind of question relates to something chemists do all the time, making solutions, either from a pure solute and solvent, or by diluting an existing solution. So you better listen up. First, let's do a fairly simple problem, similar to the example that you already saw. Brian, why don't you read this one to us?
What is the molar concentration of chloride ion in a solution made by dissolving 1 gram magnesium chloride in water to produce a 250 milliliter solution?
Okay, now, Brian, remember that in tackling a problem like this, the first step is always to write down what we know and then what we want to know. Then we can look for steps to get from the former to the latter. So let's actually write down a list of the things that we know. Remember, the best way to solve problems is to think with your pencil.
Okay, so this is the part where I act, right? Okay, let's see. We've got 1 gram magnesium chloride. I'm writing that down. Let's see. We also have the molecular formula for magnesium chloride, which is MgCl2. 250 milliliter solution is what we want, and I think that's it.
Okay, that's all that we got out of the problem directly. Are there other things that you know, say from a lecture in the past, that are going to help you solve the problem that we also ought to write down?
Let's see, I think I was paying attention in class.
I hope.
Molar concentration, or moles per liter?
Yeah, that's the definition, and that's going to help us, I think.
Okay.
Now, the next step is to write down exactly what we want to know.
Okay, well, we want to know moles per liter of the chloride ion.
All right, good. Now let's start playing with the information we know and see if it leads us to a strategy to get to the objective. Go ahead.
Let's see. It looks like molarity would be a good place to start. Since that's a general formula, let's see if we can plug in what we know to get the answer.
All right. Here's the definition of molarity. Let's focus first on the moles part. We're going to look at the individual parts. What we want specifically is moles of chloride ion on the top, so let's put that in there. Now, we don't know the moles of chloride ion, but we do know something that would give us moles of chloride ion. What is that?
Well, we know grams of magnesium chloride.
Right. So how do we get from grams of magnesium chloride to moles of chloride ion? And by the way, along the way, let's use dimensional analysis, okay?
All right. We start with 1 gram magnesium chloride, and we can convert that to moles of magnesium chloride by multiplying by 1 mole per... Wait, what's the molecular weight of magnesium chloride?
Well, it isn't here, but we can calculate it looking at the periodic table here in our textbook.
Let's see here. This is a special calculator, so the formula weight is right here. Magnesium chloride, 95.2104 grams.
Great.
So we cancel out the grams and we get moles.
Yeah. Now, moles of what?
Of magnesium chloride.
And is that really what we want?
No, we want moles of chloride ion. So if we multiply again by moles of chloride ion over moles of magnesium chloride, we cancel out the moles of magnesium chloride.
Okay, so we've got to have a ratio of moles of chloride ion per mole of magnesium chloride. And what is that ratio?
Well, there are 2 moles of chloride ions released for every mole of magnesium chloride. So the ratio is 2 to 1.
Yeah, good. Now, if we follow the units, we've arrived at moles of chloride ion on the top. So far, so good. What about the liter part on the bottom?
Well, we're given 250 milliliters, so I need to convert that to liters. If I multiply 250 milliliters by 1 liter over 1,000 milliliters, that should give me liters.
Great. Now we have just the units we want, don't we? Moles of chloride on the top and liters on the bottom. And in the answer, we end up with moles of chloride per liter. All that's left to do is the math. And magically, there's the answer. Great. We're done.
All right.
Well, that was fun, so let's try another one, shall we? Here it is. Let's write down what we know. We know that calcium perchlorate is CaClO4 twice. We know that it's ionic and that when it dissolves, it will yield 2 perchlorate ions per calcium perchlorate. We know that in the resulting solution, there will be 0.001 mole perchlorate ion per liter. We know that we will make 500 milliliters. And we know that molarity is moles, in this case of perchlorate, per liter. Now let's start with this last idea. We want to get from there to grams of calcium perchlorate. We have 0.001 mole perchlorate per liter, and we can use dimensional analysis to go from here, step by step, to grams of calcium perchlorate. Now what shall we convert first? Shall we try going from moles of perchlorate to moles of calcium perchlorate? To do that, we multiply 0.001 moles perchlorate times moles of calcium perchlorate per mole perchlorate. The ratio there is 1 to 2. Moles of perchlorate cancel, and we have moles now of calcium perchlorate. But we don't want moles, we want grams. So let's convert using the molecular weight of calcium perchlorate, which it turns out from the periodic table is 238.9786. Now we have the units, grams of calcium perchlorate per liter. And that's what we wanted, right? No, we want to know the grams in 500 milliliters. Now there are different ways of handling this situation. You can probably see that we'll need exactly half as much calcium perchlorate to make 500 mils than we would need to make 1,000 mils, otherwise known as a liter. But a general way of solving this problem is to set up equivalent ratios. And this is a trick I've found makes sense to me and has come in really handy over the years. We create 2 equivalent ratios and set them equal to each other. Specifically, 0.1195 grams is to 1,000 mils, as x grams, we don't know what that is to 500 mils. The variable x represents the number we want to know. Rearranging this equation and solving for x gives us our answer. See, algebra really can be useful. Now you can take a different logical approach to solving this problem if you wish. Whatever makes sense to you is fine, as long as it gets you there. Let's double check, by the way, that we have the correct number of significant digits in our answer. When we do, we're done.